for posterity. Yay, posterity. And I guess I'll share my screen. And move that over here. And move up my arm. There's my arm. Yeah, that's exciting. So, okay. So, here's like a little, just a little brief thing. So the review, this is our review session for exam 3. And here's what we've covered since exam 2. So this is all stuff in chapter 3. I might actually even, and what I meant to do in here, I'm not even sure how to do this. I'll do this over here. So we will make some bullets here. So we have our rigid body motion, angular kinematics. We could say that there's general kinematics, and then there's constant velocity or constant acceleration. It could be some sub areas in there. Then we have RBM velocity analysis. And we could break this down into vector math, what I call the 3-diagram method, which is really, and then we also have ICR, and in RBM acceleration, spelled wrong. There you go. I spelled that wrong a lot. I want to be able to do it for vector math, not matho, but math, and the 3-diagram method. We also might even include in there moving frame of reference, which is Coriolis, but don't be alarmed. We're not going to ask a question like that. I had actually thought of, I think I was it was while I was going to sleep last night. So that's right. I dream about dynamics. It's true. And you can feel free to laugh, by the way. And if you don't laugh, I have a laughing button. So I have my own laugh button there. That was for remote classes. But anyway, I was thinking I could ask questions where I showed a bunch of different diagrams and circle the ones that are that contain Coriolis acceleration or something like that, instead of doing a problem where we actually have to calculate anything. So anyway, here is on the equation sheet. This is where, let's see, and this is an old equation sheet, so I should probably pull up our current one. So let me do that. Oh, I see. I see what I did. Okay, let me move this over. So in our course information, ooh, look how slow the internet's going. No, it's not good. We have our equation sheet. You guys can still hear me, right?
Yes, sir.
Yes.
Yeah, and I have my I have 2 monitors. So on my second monitor, I have so I could see your chat things if you happen to have any things that you want to ask via chat, or you're welcome just to interrupt me anytime you want to. I don't mind that. But this is right here is yeah, this is where we're starting on our equation sheet. And so here are some sort of like general stuff. Like here's our fundamental angular kinematic equations. And then here's the ones for specific where we have uniform rotation. So we have like constant angular velocity. And then we have the case where we have constant angular acceleration. Then we have, here's our like main equations for that we generally use. And then here's ones that are specifically for when we have that relative motion inside there, right? So that's where we have like sort of like the equivalent of R dot and R double dot. that might be contained. So there's like the and here's like the Coriolis acceleration right in there. So these are like the main equations on our equation sheet that we're going to use. And for different problems, here's like, you can see that these are arranged with old exam problems for September 2017. So this is an angular kinematics problem. Here's a velocity analysis problem. I got angular, not angular, but acceleration analysis problem. Another angular kinematics, another velocity analysis, acceleration analysis.
Sure. This problem, S13, I was struggling with it.
This one right here?
Yeah.
Yeah, can you go over this one, please?
Yeah, I wrote this problem, I remember, back in the day. So hopefully I'll remember how to solve it. So let me see. How do I want to? I'll put this over to the side. Maybe I'll just write this stuff down here on my sheet. So we have a 15-inch radius flywheel, and that's a real thing, right? A flywheel on an engine, but it's 15 inches, and it's rotating at 1800 RPM. It starts out with clockwise, and it's subjected to a variable counterclockwise torque at time t0, and that torque creates an acceleration, producing a counterclockwise deceleration of -4t radians per second squared, where t is the time in seconds, and we want to find the time to the time. So when it has a rotation to 900 RPM, that's still clockwise. So it's reduced from 1800 to 900, and the magnitude and acceleration of a point that's on the magnitude of the acceleration at A at omega 900 RPM. And the time required for the for it to completely reverse, which essentially means that it's
Sure, we cannot see what you are writing.
I know. I need to see it first before.
Okay.
So I was keeping it up on the screen. My other option was to flip it onto the other screen, but here I needed to write all that stuff down first.
Okay.
Or actually, I probably could have. I do have them actually printed out here somewhere. So let me look at my cheat sheets as I'm going through here. Why not? All right, that's totally valid. I have it here in front of me here. Ooh, and I actually typed these out. That's me. Okay, so the first thing I would want to do, because I have RPM and I have radians per second squared, I might want to turn this one and that one into radians per second. So here's my initial right here. So I'll say this is going to be, to turn something into radians per second, I'll say 1800 revs per min. And every revolution is 2 pi radians. So that's 2 pi radians per rev. And then we're going to divide through by 60 seconds per min. And so we're left with is 188.5 radians per second. And we might as well also do this one over here. We just have to divide that by 2, right? So that just ends up being 94.25. All right. So our big idea here is we can see that this acceleration, deceleration, right? It's is going to be negative, just to indicate that it's decelerating. But or we could also have gone and drawn an arrow and said that what we mean by this is that it's going counterclockwise. So what we want to try to find, the time, and this is a function of time. So that's probably an indication that we want to use this relationship right here. So we'll say d omega is going to be equal to alpha dt, and we can integrate these from our initial velocity to the whatever one we want to find, and we're going to start at time 0 and go to time right there. So plugging this stuff in for right here, we end up with omega minus omega, integrating that, is going to be the integral from 0 to t of negative 4t dt. And so the integral of that is simply going to be t squared, right? So it's going to be negative 4 divided by 2 t squared. And it's going from 0 to t, so we don't even need to do the limits, right? Because 0 would just be there. So that's what that's going to equal. So we could find that omega is going to be equal to omega naught minus 2t squared. So we could find that 94.25 equals 188.5 minus 2t squared. And I believe that t is going to be equal to 6.86 seconds. And now for part B, we want to find the acceleration of this right here. So one of the things that we can find out is the acceleration at that time, the angular acceleration at that time, now that we know the time. So I'll even put that as 6.8. This should have been 6.865, I think. Is going to be a negative 4 times my 6.865. And we end up with a negative 27.46 radians per second squared. So the tangential acceleration of a point on here, and I guess I put the point like right there, right? It's going to have, well, okay, so it's rotating in this direction, that omega, but it's going to have a tangential acceleration that's in that direction, right? Because this is actually, the acceleration is that way. It's also going to have a normal acceleration in that direction. So the tangential acceleration is simply going to be the angular acceleration times the radius, and we don't need to necessarily have that negative in there. We know that it, from where they're showing the thing, it's going upwards. But I'll leave it in there. It doesn't matter. And the radius is 15, so that's going to come out to negative 411.9 inches per second squared. And then the normal acceleration is going to be that omega squared r. I almost hit the wrong one. Oops. So the omega of the thing at that time is 94.25 squared and 15. So we end up finding we had 133,200, wow, inches per second squared. I should have probably tried to fix that to make that, so because this is so much bigger than that, its magnitude isn't really going to really change all that much. So we have that the magnitude of the acceleration of A is going to be the square root of those two accelerations. And like I said, this being such a huge number compared to that one, it's not really going to affect things all that much. So with 3 sig figs, I think actually probably I left with 4 sig figs. It would have made it look. All you really find is you get the same number, right? Basically, it didn't really influence it because it's so much smaller. So that's going to be the answer to part B. And then the part C wanted to find the time required for the flywheel to reverse its direction. So all we need is to come back up to this answer right here, which remember that was -2t squared. And all we have to do is plug in the value right here. Remember, well, okay, it's this equation right there. That's the one. So just take that equation, move it down, and say 0 is equal to 188.5 minus 2t squared, and we'd find that the time for that to happen would be 9.71 seconds. So this is a lot like that the first class of the semester, right? This whole topic, because we're dealing with just these fundamental relationships, and in this case, this was the one to use for the fundamental relationship. Does that make sense?
Yes.
Yes.
Okay, who else do we got? Jacob, are you here? Whoops, what happened here? What did I
Yep, I'm
just do?
here.
Okay, good. Just
Sir,
what's the yes?
also
Yes.
the problem, the one after this one, S13 acceleration analysis, because it has 2 fixed areas, it goes in, I mix up my solutions, so I don't know if I'm correct or not.
Okay.
Yes, this one.
Let's see. Let me take a look at write down the basics of the problem here. Let me yeah, that's okay. All right, so I'll guess I'll do it while you see my camera, because that'll make more sense. All right, so we have a piston right here, and we have a piston right here. And this one has to go horizontal. This one has to go vertical. And so I can just move the camera right there. Okay. And what we're given is, okay, so this guy is C for some reason, and he's B. And here's A. And we're told that this is 60 degrees. And these lengths are 1.8 meters. I always try to think of like how big this thing would be in real life, you know, and like and what that would look like, and what its function would be. That's pretty big, right? They're 3.6 meters. That's a long doohickey. And let's see. We were given that this velocity is C is 0.4 meters per. No, I said 0.4 and I wrote 0.5. 0.4. And it's decelerating at 0.2 meters per second squared. And what we're trying to find is the angular velocity, and trying to find the angular acceleration, and then also find the acceleration at point A. All right. So this seems like a pretty long problem, but it was a problem during an exam. And by the way, it was a problem during an exam that was 50 minutes long. As all these classes at Coast Guard were 50, and the exams were 50 minutes long. This is my friend, Dr. Alicia Garcia. She had an office right across the hall from me. Very good, fun coworker. So what we start with, we need to know this right here. So I think we weren't told how to do it. So ICR seems like a really good way. And so I'm going to redraw the thing instead of trying to write on top of it. But we know that this thing has a velocity going this way, and this one has a unknown velocity coming that direction. So we want to draw like a line that's perpendicular to that and a line perpendicular to that. So that means that our ICR is right there. Does anybody have any confusion as to how to find the ICR? It's an important thing to practice, just to make sure, and it's pretty quick and easy to find it. It's usually a lot of times the difficult thing is when you have to do some geometry to find the lengths. But this one's not too hard because this thing is at 60 degrees. So that means that this is also 60 degrees right here. So this distance from C, so this is RC with respect to ICR. And so RC with respect to ICR, we can be found by just taking this length and taking the cosine, right? So 1.8 times the cosine of 60. And I do believe she didn't like to do things she didn't like in between steps. Oh wait, let me see something here. Did I do that wrong? Or did she do it wrong? Could she have done this wrong? She's saying, oh, she said the sine of 30 is the same thing as, okay, duh, I got you. I just looked at that really quick. 1.8, yeah, it should just be 9, right? 0.9 meters. So we know the velocity of C is equal to omega CBA. I usually go alphabetical order myself, but that's okay. Times RC with respect to ICR. So we can find omega CBA by taking the velocity C and dividing it by this. So we have 0.4 divided by 0.9, and we get 0.444, probably 4 radians per second. And we also know that it's going to be counterclockwise. So in our answer, we want to make sure that we indicate the direction of the thing. Now we got to do the acceleration to be able to find this right here. So our best bet is to go a 3-diagram method here. And this one probably won't be too bad because we have a lot of still we have it's going to be like aligned with an axis. So here's the one that we know. We know the acceleration at here is 0.2 going that way. And we know the acceleration of this one has to be along this line. So we're going to try to find this acceleration at B by taking the acceleration that we know at C and adding the acceleration of B with respect to C tangentially plus the acceleration of B with respect to C normally. So if we're going to apply both of those at both locations, both of those, okay. I guess I decided to go with the value on there. Sometimes I'll go with the symbol. Maybe I should have gone with the symbol. I don't know. But that means this is the one. If we're using that as the reference, that's where it gets pinned. We're going to have an acceleration component this way that we're going to know. That is going to be the acceleration of B with respect to C in the normal direction, which is that omega CBA squared times L, call it BC. And we could find the value for that, which I think is, I like to do that. It's a little easier. So we're going to take that 0.4 squared. Whoops, yeah. 0.4444 squared times 1.8. And square it 1.8 times, and I think we get 0.3556, and that's meters per second squared. Yeah, Dr. Garcia likes to do this kind of thing where she would solve stuff and she'd just leave it as a fraction. That used to drive me nuts. I can't stand that. But I believe that 16/45 is the same value. Yeah, but just a little weird. And then also we're going to have a acceleration. And we don't know which way this acceleration is going to go, whether it's going to be clockwise or counterclockwise. We could actually guess in this situation, and I think sometimes that's a really good idea. But I generally will go with a counterclockwise guess instead of trying to reason it out. So here we go this way. If that's the case, then this acceleration would be down this way. And she did like a really weird thing where she guessed she draws it the other way, but oh, it's just the way it is, right? So right here is the 60 degrees, and right here is the 60 degrees. And this is the acceleration of B with respect to C tangentially, which is alpha CBA times LBC. So I'm going to write out for my equation down here. It's best, I think, to use the y direction because we already have the value of the y direction right here. So actually, no, it's probably going to be a little easier, a little tiny easier. Yeah, maybe. We'll go the x direction. And we're doing it for what? No, it's going to be easier in the y direction. I'm sorry. I just took a peek at hers and I was like, she did the x first, but then she left it as a variable. So we're going to take our negative 0.2, because that's what we have, right? And oh, no, excuse me. All right, sorry. Get my head in the game. We were writing this equation for the spot. So in the y direction, it's 0. There you go. Get your head in the game. All right, so this is going to be negative 0.2. This guy is going to be negative, because this is drawn in the negative direction. Alpha CBA times that LBC, and I'll leave that as 1.8. I'll go ahead and put that in as 1.8. But this is really important. Only the cosine of 60 of it, right? Because it's only the vertical direction of this thing. And then now we have to have this component too, which is going to be upwards, and it's going to be times the sine of 60 degrees, because we have 60 degrees right in there. So it's going to be plus 0.3556 times the sine of 60 degrees. And if we do that, I think, I see. I think she made an assumption that it was in the clockwise direction. So that's why I think she's going to get a negative answer, because it ends up being in the counterclockwise direction. So my guess is better than hers.
So the sine 60 there is like the direction of.
It's this one right here.
Yeah. It's not cos 60.
This one should be cosine of 60, right? And this one should be sine of 60.
Oh, we took it from the one down. Okay.
Because that we were taking care of this guy right here. That's what these two, right? So we have to go up to this one. This is the normal acceleration that's at part of that point.
Our like
And
starter point is not the X there. The X. It's okay. Okay.
yep,
Yeah.
we're doing Y. I confused it by jumping back and forth in my mind.
I didn't see
there.
the Y. Sorry.
No, no problem. So I want to get the number myself. So I'm plugging it in, and then I subtract out 0.2, and then I have 1.8 and 60 cosine times, and then I can divide, and sure enough, I get 0.1199 radians per second squared. When you see her solution to the thing, she does a weird thing where she, for whatever reason, she decided to choose her guess was clockwise, so she ends up getting a negative number. But I think if you don't know for sure which direction it's going, just assume counterclockwise, my opinion. So here, you don't actually need to do the X direction because we answered part B. And if it's on an exam, don't answer something that you don't need to because that just takes up time, right? What we need to do now is find the acceleration at A. That was the part C in this. And instead of reusing this diagram, which could save time, but it could also cause you some confusion, I would personally, I would take the time to redo the diagram. And I also think in terms of like working through a problem, it might make, I just want to avoid the confusion of having it written out twice. I'm going to write the equation over here so I can finish this on one page. But what we're doing here is we know this acceleration right here. I'll put it in as 0.2. And here's the one that we want to get now. Now we don't know the acceleration either of anything on this. We don't know it. So here is my technique, and you'll also see Dr. Garcia did it right there. I'm just going to choose these as AAX and AAY because I'm going to write out the equations for them. So I'm going to apply what I know at both the locations of the 0.2. And then once again, I'm pinning the stuff that I'm using as the translation. And now what we're going to have is we're going to have an acceleration here. This is the acceleration of A with respect to C in the normal direction. And we know this acceleration, that's this way this time, right? That's CBA. I should have labeled this. So here we go. We'll be able to find the acceleration of A with respect to C, the tangential direction. And I'm writing an equation for this location here, which is going to be the acceleration of A is going to be equal to the acceleration of C plus the acceleration of A with respect to C tangentially, and A with respect to C in the normal direction. That's 60 degrees there. That's 60 degrees there. And we know that this guy is going to be omega CBA squared L AB plus L A BC. And then this guy is going to be alpha CBA LAB plus LBC. So here we got 0.4444 squared and 3.6. So we get 0.6 0.71, really 10. And that's meters per second squared. And this one is going to be 0.1199 times 3.6, or 0.4318. So in the x direction, we have the acceleration of a, x, is equal to 0, because there's nothing in the x direction here. And this is positive. We want this one, plus 0.4318 times the sine of 60 degrees. And then we go to this guy, and it's going to be plus because he's in the positive direction. 0.7110, and then this one's going to be the cosine of 60 degrees. So if we do that, let's see. I'll go ahead and find it out because my paper didn't print all the way down. So times. So I got 0.7295 meters per second squared. And then in the y direction, acceleration of y, almost certainly going to be downwards, but I don't know that for sure. We're going to get a negative 0.2 because it's shown right there. Then we're going to get a negative 0.4318 cosine of 60. And then this was positive because it's going upwards. So 0.7110 sine of 60. So 0.2, make it negative, and 0.4318, 60 cosine times, make it negative, add them together, and then 0.711 times the sine of 60, and add them together. Oh, surprisingly, it's positive. 0.1. See, I'm looking at this answer here, and I'm thinking I must have messed something up somewhere along the way. I'm looking. Yeah, this should be a larger number, I think. I might have messed something up there. I'm feeling as though I messed something up right here. Let me double check that value when I get here in a second. I got 1998. So what did I do? 0.4318 times sine of 60. All right, and then 0.7. I don't know. Yeah, I get a different thing than she does. I think I'm right. I can't believe that she would get something wrong. Yeah, I'm looking at her values right here. For some reason, she's got 1.796, and I don't think so. So she's got that same value right here in the sine of 60. Yeah. So I just don't think that's correct. Why hasn't someone figured this out before? Maybe somebody has. Maybe I fixed this. I don't know. This is an old printout, but anyway. So you could either write the acceleration of a. I'm sorry. Osama, were you saying something?
You are correct, sir. I did the calculation too. Your result
Okay.
was correct. I was muted and I was talking.
She and I had the kind of relationship where I could like pick on her maybe, but I wouldn't. I'm too nice. I'm not going to pick on her.
Mhm.
Like, why? Look, you made a mistake, and you look. Nah. Mistakes happen all the time. People make mistakes all the time. So this is also going to be 0.756 meters per second squared, and it's going to be an angle going upwards. But no, it's 756. I'll give another sig fig right now. And so it's going to be 0.1998 divided by 0.7295, and take the tan of that, so I get 15.32 degrees. That's just an extra step, but yeah, you know. I try not to make problems as long as this. This is a pretty long problem. Worth 30 points, so there was you know, at least two other problems. I could even look that up, couldn't I? I could look that up if I had my mouse someplace where it was useful. Why the hell are you all the way over there? All right. We don't need to do this. Okay, so is there somebody have another request?
Problem S14, velocity analysis. Now we did the acceleration. We did the how do you call it? Angular kinematics. We do one velocity and we have a whole idea.
Okay. So which problem you were asking for?
S14.
Yeah, I don't necessarily have them in order. So is it before this one or is it after this one?
After.
Professor,
Yes.
I have
Yes,
to go. Are you available Monday for office hours?
Yes. Every day. Yeah.
Okay, I'll get a pile of questions ready for Monday. Thank you.
Okay. Cool. But make sure you're practicing some problems. Okay.
I promise I will.
Okay. Good. So which problem you're talking about?
I think he means it's two problems after the one we just did. Is that what you mean, Osama?
This one, yeah, the first one. The one it has a and B, like the point B and A.
So this is the guy?
Yes.
Okay. Yeah, and I could tell that I was the one that wrote this or modified this, I should say. Because I don't know, just looks like something I would do. All right, so let me see. Not sure what the difference is. Oh, no, it was her. It was actually Dr. Garcia. Okay. So in this one, we're just asking about the velocities, right? And it's got a little slider thing acting right there. And the little part that's going right here is constrained so that you know that this thing has to go left and right. And 192 millimeters, which is a weird dimension. Must help something somewhere. And this is 360 millimeters. And this is 240 millimeters. And then I think just to save some time, kind of like already kind of told you that this kind of gave you sort of where the ICR was going to be. I think that's cheating. That's okay. kind of told you this was 34.71 degrees. You could figure that out on your own. But here's like the first. This is the angle that really mattered more than anything else. Is the 30 degrees. So what we were trying to find here was acceleration of AD, not acceleration, angular velocity of AD.
The second angle is not 39, it's 34.
What did I say? This one?
Yeah, we have a 34 in the.
Oh, it looks like a 39, doesn't it? There you go. That's what you mean?
Yeah. It was
okay.
looking like a 9.
It was just an ugly 4. But,
Yeah.
but I probably would have misinterpreted my own handwriting. So thanks, because doing one of these things, never mind. Okay, so we want the magnitude and directions in all of the answers, so be careful with that. She just went ahead and jumped through. I don't like to. First off, I don't like the fact that we have that angle right in there. I would have like totally calculated that for you, but that, I mean, made you calculate that. But maybe I'm a jerk. I don't know. But this velocity right here must be coming up and down, and this velocity here, very similar to that other one, must be going left and right. So when we get to this, we go, this right, here's a line going through this line of action velocity. Here's another one. Oh, by the way, I can't remember, which one did they give us in this problem? I should have looked and seen. Knowing that at the instant shown velocity of the collar is going 1.6 upwards. Okay, so that's an important thing to know. VD is 1.6 meters per second. Oh, I had that. Oh, okay, duh. I see it now. So here you go. Here's our VD equals 1.6 meters per second. But here's where our ICR is going to be. So that's going to be an RD with respect to ICR. So, and once again, this is 30 degrees. So RD with respect to ICR is going to be that 360, or this is in meters, so I should make this into meters as well, times the cosine of 30. And she does a weird thing where she loves to write the square roots of things. I don't know why, but it's okay. So we get 0.3118 meters. So if I want to get, I get the velocity D is going to be omega, I guess we're calling it AD, times the RD with respect to ICR. So we can find our omega AD by taking that velocity D and dividing it by the RD with respect to ICR, or 1.6 divided by 0.3118. And I get 5.132 radians per second. And recognizing that that means that it's going to be rotating that way with our omega AD. All right. So in order to find the R, I guess that point is called B. That's B, and this is A up there. So there's B. So we're gonna have the B with respect to ICR. We notice that the velocity is going to be coming that way, our VB. So our RB with respect to ICR is going to be our 0.360 times the sine of 30. So that should just be 1/2 of it, right? I don't know why I put that in parentheses, but I did. So we're going to get the velocity of, did I just mess that up? No, I think I'm okay. All right. Velocity of B is omega AD times RB with respect to ICR. So 5.132 times our 0.18. So I get my 0.9238 meters per second, and we should put an arrow right in there. I didn't fit it over to the side. Now the challenging part is to get this guy right in there, that distance. Let me draw him again. I mean, it doesn't kill me to redo this. I'm looking and seeing what she has done and going, what the hell did she do? I'm like, okay. So a lot of times for me, it's just like breaking things down into all the triangles that I possibly can to try to find things I want to know. Okay, so they gave us this angle right in there, which was kind of nice of them, but I don't think I need it. Personally, I think I could have found, because I have this length right here, and I have this length right there. I have this, I found a minute ago of 0.3118, and I know this is 0.36. I just turned that into a 6. And then I also know that this is 0.24. So if I want to find this RAICR, I could use the law of cosines to do that. Anybody remember the law of cosines? Good one to memorize. If you have, let's say, I'll call this A, B, C, then that makes this A, that makes that B, and that makes C. So the law of cosines says, in this case, I'm going to write it for B. I'll write B squared is equal to A squared plus C squared minus 2AC times the cosine of B. Right, so the pattern always goes like that. That's almost like the hypotenuse would be for a right triangle.
Yes.
But now you go ahead.
No, I said yes only. I was there.
Okay, no problem. Also, let's see, pointing that out that this is on your equation sheet right there, right? Although they, I don't know why it worked out this way, but they decided to go, I guess it's sort of my fault. We decided that we would use alpha corresponds with A, and like maybe beta would correspond with B, and I'm not sure what would correspond with C. I don't know my Greek letters well enough. But the idea here is that we could get that RA with respect to ICR by saying the square root of 0.3118 squared plus, what does that end up being, 0.5? I think that's 0.5 squared minus 2.
You said 0.6. The overall from.
Oh, it's 0.6. You're right. Yeah.
Yeah, 0.6. I just calculated it.
Thank you, because I can't do math. And still, I was able to succeed at least this far in life. 0.3118 and 0.6 times and 2 times and cosine of 30 times, and then you subtract it. No, I think I screwed that up. 0.3118. I'm going to do it again. 0.6 squared and add them together. I get 0.457. Okay. And then 0.3118 times 0.6. Great. Times 2. Great. And then 30 cosine times. And then I subtract it. Yep. Oh, I did it right before. Square root it. And I get 0.3650 meters. And she got the same thing. So woohoo! And so therefore, the velocity of A is going to be equal to omega AD times R A ICR, or 5.132 times 0.3650. And I get 1.873 meters per second. But we needed the direction, and that's a little bit more challenging. I mean, we'd actually need to know what these angles were. So that's one of the reasons why she probably gave this angle as part of it right here. Because, well, for one thing, let's see this thing. We know this thing is moving this direction. So it's going to be a velocity that's like that right there. I'm trying to think my way through this. So I think in terms of velocity, yeah, okay, so this is 90 in between here. So this ends up being the 34.71. So the velocity of A is equal to 1.873 meters per second at 34.7 degrees. 1.
Sir, but how did you get the direction? We know it's doing that. That's why I like the BA.
Well, I could get the kind of I could get it sort of from the ICR, right? I know that I have this angle right here, so I know that it has to be perpendicular, and I didn't do a good job of drawing it perpendicular, by the way. I don't know why I messed it up. I'm trying to think how I got that messed up. It should be perpendicular to this.
Okay, now it's clear. I was thinking it was an angle X. Yeah, now it's more clear.
Yeah. Now it should be clear. Yeah. I think I accidentally took it against that one. It should be that one that is perpendicular to. Yeah.
Yeah, I need to solve more problems.
Yeah, well, it definitely, you know, the little minute things can sometimes mess you up, and they could really, it's really helpful the more problems you solve. Something I haven't pointed out enough, maybe, and I've been thinking about, like, you know, really encouraging this because it's, you know, these are fresh problems. We have a whole new, a whole set of them. I've been meaning to use them, but under my useful links and resources, if it'll open it up, at the very bottom here, I have on this website, or a link to a website right here. See this guy? Old exam problems from Missouri University of Science and Technology. See, I'm going to open this up in a new tab. My internet connection's slow. Anyway, they got a lot of exam problems on here. And I went ahead and just for, hey, you know what? I thought it would be useful. I went and collected them and put them in order for our exams, right? So they have other things on there. They didn't necessarily. So this, would you see here, this link or this page right here? This is, I just collected a bunch of them. I don't even think I collected all of them, but these are all like additional problems to try out. They're from other. They're from. I'd like this one. Looks like he might have made it himself. I don't know. But you know, these are also problems to try out. And one thing I would caution though is if you go to look at his solution to some things, he takes like he uses a method that we're not using, especially for acceleration analysis. Like for this guy right here, I know what he's doing, and I don't think it's like going to be helpful to try to teach it. It is like a very simplified thing, but you can take a geometry thing and take the derivative of it. But I guess you could find using our method, you could compare the numeric answer. His numeric answers, I'm assuming, should be correct. But I'm just telling you that there's like a ton of problems, right? So like you can go through, and these are all simple enough problems to be able to do during an exam, right? That's the good thing about these, right? That you should be able to they're short enough that you should be able to do them in exam. And you can see that some of them are almost identical to the ones we've been doing, right? You know, but just something I would point out that you got even more problems solved if you want to challenge yourself and really see if you're ready. And I'm not above trying to steal some of those myself for exam questions. Other types of problems or other problems you want to see some more examples of?
I still didn't see the other problems because I only like reached this area. I still didn't go to the other half. So
You can see my screen though, right?
yes, yes.
Is that what you mean? Okay.
I'm talking about exam prep because I didn't see all the problems. I couldn't solve all of them now, so I don't know.
Oh yeah, yeah. I understand. I'm just suggesting that there's another source of problems that are worth.
Yes.
If you want to challenge yourself, and yeah. So what about some of these? Want to take a look? I also had. I think these might actually be not in our packet. Let me take a look at our packet.
I don't remember seeing this one.
Yeah. So it's this is a typical kind of problem. Let's see. I don't know why I have it in here. I must have. This is the same problem. Why do I have it on there twice? 3 times. That's weird. I have the same problem on there 3 times. Is there anything on there? No. All right. I must have really liked that problem.
So for me, I will need to go. Like I need to solve some more problems, and
Okay.
yeah.
Oh, that's totally fine.
Okay.
I gotta see why I have. I just found this thing. There's the same stupid problem again, isn't it?
Mm-hmm. Have a good evening,
No,
Zach.
It's just different things. All right. So Zach, it's just you and me. What? Oh no, there's somebody else here. No, that was some.
Can you go over? It's the third problem in the exam review. Looks like a lot of components to it.
This guy?
Yes.
This is, actually this one is very much, really, even though it has these 2 things right there, there's really only one part to it that's moving.
So I see that actually. Wait, actually, is there any vector math problems in here that we could go over? Just to refresh my mind.
Sure, we could turn any of them into vector math problems too, if you'd like. Like we could turn this one in here. We could do it. Let's do this in 3 different ways.
Okay.
This problem right here. It's a little bit overly simplified because this thing is horizontal and this one's vertical. But I mean, that's not a terrible thing to have it simplified, but it's kind of, I don't know. I want to learn, during an exam, I don't mind making something simplified, but during exam prep, I don't want to make something that's, where you lose the opportunity to figure something out. But let's go ahead and try it all three ways. I think I'm going to start out with my vector math, but
Okay.
let me write down the nature of the problem right here. Okay, so it's going up at this 40-degree angle, and so I'll draw it up here, draw the piston up there. And here's our connecting rod. Oh, look at that, screwed that one up. I think my kids came home. Both kids.
You got a full house now, huh?
Yeah, the dog's gonna be so happy. Oh man, the whole family just everything we do is about the dog now. She runs the house.
Yeah, same with my family. Anytime we like even go out to eat, it's like, oh, we gotta hurry up and get home to the dog.
Yeah, she loves to run in circles and bark like mad as anyone leaves. It's like, how dare you? How dare you? It just spins in little circles. All right, so the first thing, in terms of vector math that we're going to try to do, our goal is to find the velocity of c. All right, so we're going to march through it with what we know. We will write this first one as negative 5k, right, radians per second. And then we have the position vector that we're going to use. So in terms of a vector equations, we're going to use this equation right there. That's basically, we're just going to keep using that one over and over again, right? That guy.
Okay.
So here's in our first thing, let's see, this is B and A and C. So we were going to write out what the velocity of B is going to be. The velocity of A plus omega AB K crossed with R B with respect to A. So we should write out R B with respect to A, and that's just going vertically. So all that's going to be is 0.3 J. So, and we know that that is going to be 0, right? The velocity of A is 0. So velocity of B is really going to be our negative 5, right there, K crossed with our 0.3 J, or negative 5 and 0.3 and K crossed with J. And we know K crossed with J is a negative I. I think my wife is texting me to say that one of our kids is home. Now, Andrea says, you sound busy, but love you picking up some things, and let's get lunch sometime soon. So you got to interrupt everything you do and say, yes. Okay. And so here we're going to have the velocity of B, as we would expect, is going to be negative and negative, right? Negative, negative. It's going to be positive, so because it's going to go in the x direction, right? So that's just going to be 1.5. I didn't need to put the brackets around there. 1.5 meters per second, obviously, on there. Okay, and then, but I'm just strictly going by vector math, right? I'm just trying to be very methodical in there. And then we're going to say the velocity of C now is going to be equal to the velocity of B plus omega BC K crossed with RC with respect to B, right? And we don't know the omega of this. In fact, that's one of our find, right? We want to know that's like one of the goals that we're looking for. So we're going to assume it's positive. We can write out this equation, which is really boring. That's going to be 0.5 I. So we'll say the velocity. Okay. So one also thing in writing this, we know the line of action of C, right? So we could say the velocity of C is going to be equal to the speed of C. And let's assume it's positive. We're going to assume it's going up in that way. We could also assume it's going that way if we wanted to, and just see what we get when we get to the answer. But it's probably best to choose the positive one. So we're going to take the cosine of 40 degrees I plus VC sine of 40 degrees J. And maybe I'll even like just to have some numbers to put down instead of carrying the thing around there. So 40 degrees, whoops, turn it on. 40 degrees cosine is 0.7660, and 40 degrees sine is 0.6428. So we're going to put that over there onto the side. So we go 0.7660 VC plus 0.6428 VC, I, dummy, J, is going to be equal to omega that we don't know. No, we got VB. We know that VB is I. Forgot to put that in there. So, 1.5 I plus, and let's see, I'll skip a little bit by going omega BC times 0.5, and that's going to be K crossed with I, which we know is J.
It's J, yeah.
So the easiest thing to do here is to do this in the I direction first and say 0.7660 VC is equal to 1.5, right?
Yes.
So we're going to get VC. So we could actually answer the second part first in part of that. So we have 1.5 divided by that. So we end up getting 1.958 meters per second. And then for J, we get 0.6428 times that, 1.958. And that's going to be equal to omega BC times 0.5. So we get omega BC. Boom, and then 0.5, boom. And I get it as 2.517 radians per second. And I got positive, so that must mean it's got to be counterclockwise, right? So that's like the vector math portion of it. If we were going to do that same problem by way of ICR, it's actually fairly easy to do. I'll rewrite the thing out here. We know this thing is going that way, and that's 40 degrees. Well, first off, you know, the first thing we would do is to get this velocity right here of this guy by itself, typically in an ICR thing, and we know that. So we just know that we're going to take this is going to be velocity of B is 5 times 0.3 or 1.5, right? And then we're going to stick it and put it onto this guy. I don't know if I left myself enough room. We know this is the velocity is coming this way on that. And so it's where the intersection of those two are going to be, ICR, right? And we know that that velocity went that direction right here. So we got our omega, call it BC. So we can actually say, oh, well, we know that this velocity of C is coming up that direction. This R, call it, that's B, ICR. Oh, got to be careful with our angles right here. This is 40 degrees right there. We know that. And so therefore, this is 40 degrees, making this 50 degrees. So our RB with respect to ICR, and we have this length of 0.5 right to there. So it's going to be equal to, and this is 90 degrees, so that makes, this is like an easy one to do. We don't have to mess around with crazy triangles. And so we're just going to get it should be the tangent. Should we divide the tangent? I think we have to divide, because this is the adjacent. We want the rise, and we know the run. So we're going to take our 0.5 and divide it by our tangent of 50. And from that, no, is that true? Wait, no, wait. Got to be careful there. We have the run and we want the rise, so we're going to multiply it. My bad. $50 tangent 0.5 times. Yes. So we get 0.5959 meters. So omega BC is going to be velocity of B divided by that RB with respect to ICR, or 1.5 divided by 0.5959. And we get 2.517 radians per second. And then we also need this guy right here. So he's going to be the R column C with respect to ICR. And so that ends up being probably the easiest way I could do this is I want the hypotenuse, right? So I could divide by the cosine, because this is the adjacent to 50. So I take 0.5 and divided by the cosine of 50. 0.5, 50, cosine divide. So I get 0.7779 meters. So the velocity of C is going to be omega BC times RC ICR, or 2.517 times 0.7779. So the velocity of C is, I can just multiply two things in my calculator. There I go, boom. 1.958 meters per second. And we agree, yay. And we said it was a velocity, so we really should also, go like that. Give it an angle too. And then using the 3 diagram method, you start out with this guy right here. We know that that's we already we already assume we already have that. So we know this one of 1.5. So we're going to place them in both places, 1.5 and 1.5. And so we're going to put this into place right here. And we know the line of action of this has to be like that right there, right? So of 40 degrees. So we're writing out an equation for this one, which is the velocity of C is equal to the velocity of B that we know, plus the velocity of, velocity of C with respect to B. And so that's, chances are it's going to be a, well, no, chances are, we don't necessarily know, but I'm going to go B, C. We'll go assume this direction. So this becomes the velocity of C with respect to B. So what I might write for this guy right here is say, yeah, I'm going to assume it's in this direction. I guess that's the velocity of C. So I write here for the X direction. I meant to make it a hyphen right there. We'll say VC times the cosine of 40 is going to be equal to 1.5. That's right there. But then we don't know anything. You know, over here, there's nothing in the X direction for this right there. So that's good. So actually, you could just say the velocity of C is going to be 1.5 divided by the cosine of 40. And we end up with 1.958 meters per second. And then in the Y direction, we're going to say it's the velocity of C times the sine, but we know the velocity is C. And there's nothing in the Y direction here, so that's fine. But there's everything in the Y direction, and we happen to know that this velocity of C with respect to B is going to be omega BC times this length, which is 0.5. So we're able to find omega BC is going to be 1.958 times the sine of 40 divided by 0.5.
I got 2.517.
Yeah.
Okay.
And that's the same thing we got in the other ones, right?
Yes.
So it's sort of like a competition as to which one's the easiest. I think ICR is probably the easiest, but that's especially made easy because that's just a 90-degree triangle right in there.
On the exam, will we have like the option of the three methods, or will you like say like use this method for certain problems?
I'll probably tell you what method I want to see.
Okay.
Because it's, want to be sure
Yeah.
that you could do it. Yeah. So there's likely to be 3 or 4 problems on the exam.
Okay.
And the longest one is always going to be an acceleration one, and I will, in the acceleration one, I'll probably give you the angular velocity so you don't have to do a velocity analysis.
Okay, that'll probably save some time. And then you said those other problems were under useful links and resources
Yes.
on the Blackboard page. Okay.
Yep. I'd only caution you about some of them are going to use methods that we're not using. So that, if you happen to run across somebody, go, man, I have no idea what they're doing. It's likely that they did a weird, they're using. It's not weird. It's just we're
No,
already
it's
covering so much that I don't want to like contribute to it by adding a new method that is totally valid, but maybe just I don't know, it's useful. I don't know. I could be convinced that maybe their way of doing the thing. I could explain what I mean by showing you the example as opposed to just being this mysterious blob of information. I think it was this guy right there. My recollection holds true. Yeah, there you go. So you can barely see that, but you'll see that he does an acceleration analysis. So I did this the other day with James. We were working through this problem, and then I said, oh, maybe I'll just look it up. And you can see what they did there is they figure out this parameter x, and they have it in terms of cosine and cosine, right? So they have this. Then they take the derivative of it with respect to the angle changing. So they get a theta dot, and then they take the derivative of that again. So they get, there's two parts of it because there's a sine of theta and a theta dot. And then they're able to get what the angular velocity and angular acceleration are going to be. It's and doing it that way is very, very quick. That's the benefit. Yeah. But I don't know about adding in, and it's really dependent on the fact that this geometry lends itself to that, right? Not every problem is necessarily going to be one that you can do, but like for instance, though, this problem right here, we could probably do something along those lines by having this parameter right here be the thing that we solve for. But we're going to have two different, but we're going to know this, the angular velocity. So that's maybe the thing. I don't know. Maybe it's a good idea. I don't know. Maybe in the future to try to introduce trying to do that. I think there are some examples in Beard Johnston where they do show doing that, but it's not the main way that they go about solving things.
Oh, okay. Yeah, I didn't see that.
Any other problems? No pressure on you to pick any more problems. By the way, I know you're the only person here, so.
No, it's all right. I don't care about being the person. No, honestly I didn't get to all of them, so I'll email you maybe later in the day or early tomorrow if I have any other questions, and I could probably come in on Monday or something, or do the collaborate.
Cool. Anytime, anything I can do to help.
All right. Thank you so much.
You're welcome. Have a great day. Okay. Have a great week. Rest of your weekend.
Thank you. You too.